Energy and charge distribution, take two. Woohoo! Okay, so let's talk about the energy stored in a charge distribution. Imagine, if you will, I have one charge here. What's the amount of work that it takes to move that charge from infinity to that location? Well, it's going to be 0, because Q1 times V1 is equal to 0, because there's no potential that that charge is interacting with. But now, if I take another charge and I move it here, charge 2, these two charges are going to interact. So work 2 is going to be equal to the charge of itself times the potential due to charge 1. So this is going to be V1, and this is going to be 1 over 4 pi epsilon naught Q1, Q2 over the distance between them, which is script r 1, 2. Right? That's this distance here. Script r 1, 2. Okay? So now if I take a third charge, and I bring it in, say I put it right here, now charge 3 has to interact with both charge 1 and charge 2. So it's going to be charge 3 is interacting with the potential. But since there's two charges, charge 1 and charge 2, I'm going to have a superposition of the potentials due to charge 1 and charge 2. So this is going to be 1 over 4 pi epsilon naught Q2, Q3 over script R2, 3 plus now, right, principal superposition, 1 over 4 pi epsilon naught Q1, Q3, script R 1, 3. Right, because this is going to interact with charge 2 and it's going to interact with charge 1. So if I bring a fourth charge, here, charge 4, now that's going to interact with the 3 other charges. So charge 4 is going to be charge 4 times the potential, which would be 1 over 4 pi epsilon naught. And now I'm going to have Q1, Q4 over script R1, 4 plus Q2, Q4 over script R2, 4 plus Q3, Q4 over script R3, 4. To find the total work that it takes to assemble this charge distribution, I have to take all of these and add them. Right? So when I do, I get the following. The total work is going to be 1 over 4 pi epsilon naught. So Q1, Q2 over script R1, 2, right, that term, plus Q2, Q3 over script R2, 3, which is that term, plus Q1, Q3 over script R1, 3, plus now these 3 terms, Q1, Q4, script R1, 4, plus Q2, Q4, script R2, 4, plus Q3, Q4, script R3, 4. Woo! That's a lot of terms. Okay, now let's think about trying to make this more of an abstract thing, right? So that it'll apply for more than just 4 charges. Let's take these 2 terms and flop them. So this is 1, 3, and this is 2, 3. So that's 1, 3, and this is 2, 3. Okay. I can take this and I can rewrite it in the following form. 1 over 4 pi epsilon naught, the sum of I equal 1 to n, in this case n would be 4, the sum of j greater than 1, greater than I to n, qi, qj, script r, ij. Let's see how this makes sense. Imagine if n was 4. As I go through the first time, my I will be 1. So my j would be 2. So here I have 1, 2. Then this one goes to 3. So now I have my 1, 3. Then this one goes to 4, and I have my 1, 4. Okay, that sum is done. I go back here and I convert that to I equal 2. So now I have j, if I is 2, j can only be 3 or 4. So I have 2, 3 and 2, 4. And then if I is equal to 3, the only one I get is 3, 4. So if I look at this at a chart in some way, if this is I, and I have 1, 2, 3, 4, right? And this is j, 1, 2, 3, 4. And that's j, right? And these are somehow a grid of points. When I is 1, I'm going to include j equal to 2, j equal to 3, j equal to 4. When I is 2, I'm going to include j equal to 3, j equal to 4. When I is 3, I'm only going to include j equal to 4. Right? Now this is great if n equals 4. You can do this. It's not a hard thing. Maybe at 4 you might want to start thinking about doing this in a program like Excel or MATLAB. But, you know, it's something where addition is easy. But now if we let n go to like 100 and we make it really big, this is what happens to this chart. It becomes 1 to 100, right? 1 to 100, right? The diagonal term, we include all of these included, and we don't include any of those, right? Again, this is I, and this is j in my sum. So we're including this bottom half and not the top half, right? But this is completely symmetric. And if I have I equal to 10, j equal to 90, that's going to be the same as I equal to 90, j equal to 10. So if I were to include these terms, I would be effectively double counting this. If I included the whole grid, I would double count. Now, there is a small number of terms on the diagonal that we're ignoring, right? But as n goes to big, as n goes to be really large, the part of that which is made up of those pieces is really small, right? So that effectively goes to 0. So if I put this in, I'm going to double count. So here, I start my sum at j equal to I. But if I turn it into a sum from j equal to 1 and I include all terms, I'm double counting. So I have to include a factor of 1/2. 1/2 times 1 over 4 pi epsilon naught. The sum I equal 1 to n. The sum j equal 1 to n. Q, qi, qj, script r, ij. Right? By including the don't terms, I have twice as much stuff. And so in order to handle that mathematically, I have to multiply the whole thing by 1/2. All right, so then I can do some rearranging. I can keep the 1/2 out. I can pull the sum with respect to I here. And then I have 1 over 4 pi epsilon naught, the sum of j equal to 1 to n qj over script r ij. But hey, isn't this just the potential? So then it is 1/2 the sum of I qi vi pi. So basically, the amount of work that it takes to build this thing up is Q times V, right? And because we're including our Q in the V that we're looking for, we have to make sure that we avoid this double counting by multiplying it by 1/2. That tells us the amount of energy stored in a charge distribution.